All right, welcome everyone to the next seminar. So I'm delighted to introduce Aurora Island, who's coming to us from Stanford at the moment. So she recently moved to Stanford after finishing her PhD at the University of Chicago. And today we're going to be hearing some exciting stuff about B modes and phase transition. So why don't you start sharing your slides now, and we can get started. So thanks a lot, and I'll hand over to you. So take it away. Thanks.
All right. Thank you. And thank you for having me. I'm very excited to share today this really interesting, these surprising results. And this is based on a paper, a project. This paper down here is the archive number that I did with collaborators at Gordon Brunjach at U Chicago and Fermilab, Yusin Tsai, who's at Notre Dame, and then Kyler Green, who was a PhD student at University of New Mexico and just graduated. Um, and I'm going to be talking about CMB B-modes from cosmological phase transitions. And if I don't know how questions work, so I'll defer to however you normally take questions.
Yeah, whatever you want. I mean,
All
people
right.
interrupt now and then, but it's up to you. Yeah.
Okay. Yeah, cool. So if you have a question, just interrupt. Um, all right. So I want to start with a quote, and I just pulled it from a random paper, but really you'll see statements along these lines in many papers, and it really um I don't know, this was the standard lore up until this embarking on this project. So tensor fluctuations are a prime target for future observations of the CMB because if detected, they can provide conclusive verification of the theory of inflation. Or slightly shorter, B-mode polarization in the CMB was seen as a smoking gun for inflation. Um, I don't know that I need to motivate inflation too much. So it, solves the horizon and flatness problems in addition to giving an origin story for the primordial perturbations that see the structure that we see today. And inflationary models pretty generically predict a nearly scale invariant spectrum of tensor perturbations. And these tensor perturbations induce a characteristic B-mode polarization pattern in the CMB. Um, there are, of course, other sources of B-mode polarization, and you'll see in a slide or so what those look like. These include gravitational lensing, which can convert the E-mode pattern to a B-mode pattern, and then dust or foreground noise, as Bicep well knows. But as of like embarking on this project, inflation was really the only direct primordial source that we were aware of. All right, so here is the plot of the angular spectrum of, well, E mode polarization, B mode, and we've also got temperature, but just concentrate on the B mode. So this is the prediction of some inflationary model with a tensor to scalar ratio of 0.03 and then 10 to the minus 3. And it has this kind of distinctive spectral shape. It's got a peak here at around a multipole moment of 100. This kind of corresponds to recombination. And then on larger scales, so smaller L, it has another peak here that corresponds to reionization. Um, and the total amplitude, of course, depends on what you have for your tensor scalar ratio, but it pretty generically has this shape. Um, and then you can also, this is what we expect for the lensing B modes. Um, so this peaks on smaller scales and has just this slope here. And then we've got some data as well. So the lensing signal, if you understand the E mode polarization spectrum pretty well, you can kind of predict what this lensing should look like. So, you could eventually delens if your signal. So this is, just generically what you would predict just from inflation and then just normal background stuff. Um, However, in principle, though, any source of, large scale coherent tensor perturbations, if they're produced before reionization, can contribute to the B mode polarization. Um, so one source of tensor perturbations that people think about for gravitational waves are first order cosmological phase transitions. And these generically source tensor perturbations in a few different ways. I think there are a few ways beyond this, but bubble collisions. So these, I'll talk about this more later, but first order phase transitions proceed via bubble nucleation of true vacuum in the metastable phase, and you get tensor perturbations when these bubbles collide and break spherical symmetry. And then even after the collisions, you have like a fluid kinetic energy that's propagating these sound waves, these source tensor perturbations. And then turbulence does as well. So first order cosmological phase transitions are another source of tensor perturbations. Very generically, these predict peak power on small scales. Um, phase transitions are typically like an early universe thing. So, when the cosmological horizon was smaller, so you're going to get peak power on smaller scales. Um, but even though, that's where the peak is, you still do have power on large scales. It's just really suppressed. It's this white noise spectrum that corresponds to just uncorrelated fluctuations. And it has this characteristic k to the third scaling. And naively, you would expect the contribution from first order phase transitions to be negligible. I certainly expected it to be negligible. And actually, the way this project got started was Gordon and I were talking, and Gordon asked about this, and I was very skeptical. So I set out to do this calculation kind of to prove him wrong, and then was kind of surprised that it looks like you might be able to see something. So if you're thinking that this source should be negligible, that is the intuition. And the intuition is it's because the CMB really cares about, long wavelength modes, large scales, like time stuff. Um, it cares about, yeah, co-moving wave numbers like 10 to the minus 2 inverse megaparsecs or smaller, maybe a little bit larger too, but the large scale stuff. And for the phase transition, if this is happening in the early universe, the tensor power spectrum is going to be suppressed on these scales. In particular, it's going to be suppressed as k tau star to the third. So here, tau is conformal time, and the star is just the conformal time at the time of the phase transition. So for the things in the tail of the tensor power spectrum are going to be super horizon modes at the time of the phase transition. And for these guys, it's this quantity k tau star is much less than one. So your power in the tail, which is going to be the thing that's contributing to the B-mode polarization, is going to be very suppressed. Um, and we'll see this more explicitly later in formulas. This is just kind of schematic at this point. Um, so that's all true. But I want to make the case that despite this, the tensor perturbations from a first order phase transition can actually produce a B-mode polarization signal. And the strength can actually even rival that of inflationary predictions if you choose the phase transition parameters right. And it's can even be on observable scales. Despite that, it's not necessarily a bad thing for inflation because the spectral shape is going to be distinct. So long as you can, measure, if we do eventually measure primordial B-mode polarization, if you can measure it on multiple scales, you can still distinguish between these scenarios. All right, so that was the motivations. Next, in terms of the overview, I'm going to go into reviewing how B-mode polarization gets baked into the CMB and how we calculate it. Then review the tensor power spectrum from a first order phase transition, and then we'll get into the results and then complementary gravitational wave signal. But before I jump into that, are there any questions on the motivations? Okay. Do feel free to stop me because I feel like I tend to speak really quickly if not stopped. Um, right. Okay. So B-mode polarization. So very generically, in the early universe, if you have scalar or tensor perturbations, these are going to create temperature anisotropies, and temperature anisotropies through Thomson scattering get transformed into polarization of the scattered photons. So you can imagine some photon coming in. There's an electron here. It's going to Thomson scatter, and then get emitted. And because the light, of course, can't be polarized in the direction of motion, only one linear polarization is going to be scattered. Um, of course, there's no reason to just imagine light coming in from one direction. You can imagine a dipole anisotropy in the temperature distribution. This actually won't give you any net polarization um, because the incoming radiation have equal intensity. What you're going to get out is unpolarized. If you want net polarization, what you actually need are quadrupole anisotropies in the temperature distribution. Um, so hot spot, cold spot coming in, Thomson scatter, and then the light that's scattered from here is going to have a net linear polarization. Um, Quadrupole anisotropies come in scalar, vector, and tensor types. I'm not sure what to call these. But the thing is, density perturbations will give you scalar. In principle, vorticity can give you the vector, but this is going to be negligible recombination, so we're going to forget about this. And then the tensor pattern, that's only going to come from gravitational waves. Um, so if you project now these quadrupole anisotropies, you're going to get a polarization pattern. And in general, it's convenient to decompose the polarization into divergence and curl parts. The divergence part is called E-mode polarization, in analogy with an electric field. Um, this pattern is unchanged under, spatial reflections. It's parity even. And this pattern is going to be sourced by both scalar and tensor perturbations. Um, and then there is the B-mode polarization. This is the curl part. In analogy with like a magnetic field, which has curl. Um, and this pattern is odd under parity. So if I do a flip, these two patterns transform into one another. And the kind of most important thing here is that this pattern is directly sourced by tensor perturbations only. You can get the B mode pattern from gravitational lensing of the E mode, but in terms of like directly sourcing it, you need the tensor perturbations to get this pattern. Which is why it's, a smoking gun for tensor perturbations from inflation. Um, right. So let's make this quantitative. The object that we ultimately want is this these CLBBs, the angular spectrum of B-mode polarization. And we go through how to calculate this in gory detail in the paper, but I'll just kind of sketch the ingredients that go into this here. Um, So we have some tensor perturbation, and this is going to contribute to the temperature anisotropy. The temperature anisotropy enters into the CMB polarization tensor, which in general you can decompose into these gradient and curl parts, and we're going to focus on the curl parts. You can expand this thing in spherical harmonics, and then you invert it to obtain these coefficients, and then these coefficients enter into the definition of the CLBB. It's the kind of 2-point function of these guys. So this is more explicitly what the CLBB is, and if you actually go through the exercise of evaluating it, you can show that it's equal to this integral over log k of the tensor power spectrum times this f of L squared, which is this horrible thing, which I'm sorry for showing this, but I feel like it's where all the physics is hiding, so I have to flash it at least. Um, right. So as I said, the P sub h, this is the tensor power spectrum, and this is this horribly complicated thing involving the visibility function and the transfer function and spherical vessels. But the way that you should really just think about this f of L squared is it's like a window function or like a kernel, and it's gonna pick out the it's gonna have support on the scales that CMB cares about, which will make understanding the spectra that I show you later. It'll allow us to understand the spectra that I show you later. But just think about it like a window function. Um, so in deriving this, I've done a decomposition of the tensor perturbation into some initial perturbation amplitude times the transfer function. And this is convenient because I'm kind of separating out, the actual physics, the statistical correlations between the initial amplitudes are going to be encoded by the power spectrum, which is, defined in terms of the 2-point function of these guys. Um, and then the evolution, which is just totally deterministic, is going to be captured by the transfer function. Um, and the transfer function satisfies this wave equation, approximately sourceless wave equation, um, which here my primes are derivatives with respect to conformal time. H is the conformal Hubble, and then K is for whichever, co-moving wave number we're looking at. So you can solve this analytically. Actually, in, the plots that I'm going to show you later, we actually use a class. So the transfer functions that class is baked in, but you can solve this analytically just to have some intuition. And this is the solution during radiation domination, and this is the solution during matter domination. Um, the important thing is just, so long as the mode is outside the horizon, this transfer function is basically just one. It's frozen out, it's not really doing anything. And then once the mode re-enters the horizon, it's going to fall off and become this oscillatory thing. Um, right. So that was a lightning review of how we're going to calculate the B-mode polarization. The main ingredient that we need for this is the tensor power spectrum. This is just completely, deterministic known physics. So the missing ingredient is this tensor power spectrum, which is what we're gonna do next. But before I do that, were there any questions on the B-mode polarization calculation?
So it, this is just a naive question. So the transfer function only depends on the cosmological history, so it only depends on Hubble, and there's no other ingredients there which would affect the transfer function depending on the different sources of the signal.
Yeah, yeah. That's correct. And it's because I've separated out this thing is gonna care about the initial thing. So this is sourceless wave equation. The source the Hij is gonna satisfy the source wave equation, and that's where all the physics is gonna come in. Sorry, did that make sense?
Yeah, yeah, I just wanted to clarify. Yeah, yeah, yeah.
Yeah, cool. Um, okay, so okay. So we're going to be interested in the tensor power spectrum from some first order cosmological phase transition. So these proceed via bubble nucleation. The whole universe is in some, metastable states. And in this metastable vacuum, you're going to get the nucleation of bubbles of true vacuum. And then these are going to grow and expand. It's going to be a competition between the energy released, the latent heat from the difference in the vacuum energies versus the thermal plasma is going to, retard the expansion of the bubble. But um, eventually these bubbles are going to collide and, merge and come to percolate the whole space. Um, so Right. So these source tensor perturbations in 3 stages. The stage I just talked about was the bubble collision phase. Um, And actually, the source of the tensor perturbations here isn't the collisions themselves. The role of the collisions is just to break spherical symmetry. Because you can't have gravitational waves if you have spherical symmetry. So the collisions are going to break that. And then it's actually the gradient energy of the scalar field, which is going to source anisotropic stress. Um, and the scalar field is the thing whose interpolating profile is defining the bubble wall. So that's the first stage. Even after that completes, you're still going to have these shells of fluid kinetic energy that are propagating through the plasma. And when these collide, this also sources gravitational waves. Um, so for most phase transitions, this is going to be the dominant contribution, actually. The bubble collision phase is only the dominant contribution for like supercooled phase transitions. And when you have a supercooled phase transition, the plasma gets really diluted outside the bubble wall. And because of that, the bubble wall can run away kind of to nearly luminal velocities. It's not quite run away because there's still, you know, frictive forces, but yeah, the that's just side notes. The acoustic phase for most thermal phase transitions is going to be the dominant source. Um, and then, if there's any kinetic energy left in the plasma, the sound wave collisions produce vorticity and turbulence and shocks. So, right, this is also a source, but the relative contribution of the source is a little bit more difficult to calculate than the others, and kind of depends on numerical simulations and how much energy is left in the plasma. Um, we're going to be focusing on a supercooled phase transition. So as I mentioned, for this one, the dominant contribution is going to come from the bubble collision phase. Um, why are we focusing on this one? Well, there's this really nice paper that actually calculated semi-analytically from first principles the 2-point function of the stress tensor from this stage, which makes all our calculations later a lot simpler. So we focus on this case just because it was the simplest option, just to get kind of a ballpark estimate in terms of, can you actually even get observable B-mode polarization from like a phase transition. In principle, I would expect if you had a different sort of phase transition that had maybe the dominant contribution from the acoustic phase or the turbulent phase, I would expect that also to be, of a similar magnitude as this, what I'm going to show you, but this is just because it was the easiest thing to do calculationally. There's no, deeper reason why we chose this.
So I have a naive question. So you've not defined a model yet. So is this all generic, or is the strength of your supercooled phase transition, or the mechanics of how this is happening dependent on the model you will probably eventually consider?
Yeah, no, that's a great question. So here, because we're just looking for like a first principles, can you even have a signal? We do it completely model agnostic, and we just pick thermal phase transition parameters. It's a good question to ask. Can you actually achieve these phase transition parameters in a realistic particle physics
Yeah.
model?
So yeah, that's a
And
good
that's
question to ask. Yeah, exactly.
yeah, that's something that I'm looking at now with students at Slack/Stanford. But pending. It looks like yes, but I don't have a definite answer yet.
All right. Okay. Thanks.
hmm No, thank you for the question. Um, right. Okay. So the first thing we need to do is we need to solve the wave equation to get the tensor perturbation. So here again, the primes are derivatives with respect to conformal time. Tilde h is conformal Hubble. K squared is, or sorry, K is just whichever mode I'm looking at. This is the Fourier space guy. And then this pi ij This is the source. It's the Fourier transform of the transverse traceless stress tensor, which is some statistically homogeneous isotropic random variable. Um, and then the other thing that we're gonna assume about the source is that it's short-lived in the sense that the phase transition completes fast relative to the Hubble rate. So here, beta, or yeah, beta is the inverse duration of the phase transition. So the ratio beta on H star is gonna be a measure of how fast the phase transition completes relative to the Hubble rate. Um, Super cold phase transitions do last a long time, but it's still, within a Hubble time. Okay, so we're gonna solve this, and we're gonna solve in two different regimes, and it'll become clear soon why I'm bothering to do this. Because naively you would think just solving during the phase transition is enough, but there's a subtlety with the super horizon modes that we'll come to in a bit. Okay, so during the phase transition, I'm going to neglect the Hubble term, the expansion, because my phase transition completes fast. And I'm going to solve this equation, which you can solve via the method of Green's functions, and you get this. After the phase transition, I no longer have my source term. The source is no longer active. But I can no longer neglect expansion, so I'm going to solve this equation, which has this generic solution, and then by matching these guys at the end of the phase transition, um, XF, I can identify what these coefficients are. I should mention here, X is this dimensionless combination of K times conformal time, and now my prime is a derivative with respect to X. All right, so this gives me a solution for what H is, and now I can calculate my power spectrum. So my power spectrum is essentially the 2-point function of this Hij evaluated at some initial time, my initial amplitude. Um, and because of the subtlety that I mentioned with the super horizon modes, it's actually going to be necessary to treat the super horizon and the sub horizon modes separately. So in the sub-horizon regime, there's no subtlety. Everything goes through just as you would expect. And I can define my initial amplitude is just my solution for Hij evaluated at the end of the phase transition. This XF is K tau F. So this is at the end of the phase transition. And when I do that, I can, do the computation on the previous slide, and I find that my tensor power spectrum takes this form. So here, kappa is the efficiency factor, alpha is the phase transition strength, which is, kind of schematic. There's a few different ways of defining it, but schematically, you can think of it as the energy released, the vacuum energy released over the energy density and radiation. And then we have a beta on H star on beta squared factor. And then here, and then this delta, you might think this is a very simple expression, and it's because the delta is hiding all the physics. Um, so here, we have, some of the thermal phase transition parameters, and then this double integral over cosine of the time difference times pi. Pi here isn't the same source that I showed you before. It's like the 2-point function of two of those. It's the unequal time correlator, which is essentially like the power spectrum, just, the two entries are at two different times. Don't worry too much about delta. The reason why we chose this particular source for the tensor perturbations is this is the paper I was alluding to earlier, where they have the computation of the 2-point function of the stress tensor, and they do this calculation semi-analytically, and you can show that, and check it numerically, of course, and you can show that this delta in the sub-horizon regime, this shouldn't be a much greater. This should just be greater than or equal to. This delta takes this schematic form. So using this, I can substitute this into this equation, and I get this rough form for the power spectrum in the subhorizon regime. Okay. All right, the superhorizon regime, this is where the subtlety comes in, and it comes in because intuitively, when you activate one of these superhorizon modes, it's kind of like exciting an overdamped oscillator. Um, so the initial condition for H is actually 0, and it takes a small but finite time for H to reach its maximum amplitude. And because of that, we can't actually define Hij in the same way as we could for the subhorizon case, where it's just, you know, that evaluated at the end of the phase transition. We actually need to wait a little bit longer. The reason for this is, remember we did this decomposition of the tensor perturbation into this initial amplitude times the transfer function. And the transfer function, while we're still super horizon, is just, frozen out. It's not doing anything. So in order to safely apply this transfer function, we need to wait until H is like grown to its maximum amplitude. Otherwise, we're, doing things inconsistently. So that's the subtlety here. And because this is evaluated slightly later, if you go through and you compute P sub H in the superhorizon regime, this is what you get. It looks a lot like the subhorizon regime case, except two things. One, there's not this K on AH star squared factor. And then two, this delta, it has a different behavior in the superhorizon limit. It goes like x to the third. So if you plug that into here, this is the behavior that you get in the far superhorizon regime. Yeah, and there's two things I want to point out here. One is that this has the expected k to the third causality limited scaling. By causality limited, I just mean that these are modes whose wavelengths are much larger than the spatial correlations of the source. And because of that, it's actually kind of agnostic to the microphysics here. It's just this, universal scaling. It's called white noise. And then the other thing is that this is going to be really suppressed because for these super horizon modes, this combination K tau star is much smaller than 1. This thing goes like that to the third. So as promised, it's suppressed. Right. Okay. So we solved in the subhorizon regime. We solved in the far superhorizon regime. Now to get the full spectrum, we got to match them up somewhere. So the peak of the spectrum is going to be set by the maximum bubble size, which you can show is, given by this tilde level relation. And then if you do it a little bit more carefully, you can show that the peak wave number is this. So overall, it looks like this. Our tensor power spectrum has this scaling in the far subhorizon, or sorry, far superhorizon regime. It has this scaling in the subhorizon regime. And then technically, this only holds in the far superhorizon because we made some approximation. So, we got to map them up somehow. So there's, some interpolating region that we're not entirely sure what the spectral shape is, but we just choose the simplest thing to make it a power law. Yeah, and this intuitively corresponds to modes that are subhorizon but super bubble. You'll see in a second. It doesn't really change our results at all. So this is the equation I showed just plotted for two benchmarks. And these are the benchmarks that I'm going to focus on for the remainder of the talk. So here, the green one, this is here, the T star is kind of just like a proxy for time. So this is something that's occurring in the dark sector. I mean, you can't do this in the standard model at 1 eV. There's so many constraints. So it necessarily has to be occurring in a dark sector, but it's going to be occurring at a time that corresponds to T star of 1 eV in the visible sector. So this is the time, and then the alpha, the strength. Oh, I guess maybe I could look here. The strength is 3 times 10 to the minus 5. Why is it that small? We needed to make it that small to avoid various constraints. You would expect a larger value of alpha for a super cold phase transition, but to be in accordance with the constraints, we have to make it this small. And then we're taking kappa of 1. This is consistent with that value for alpha. Um, and then beta on H star of 2, which is very long. So again, it remains to be seen. Can you actually realize these parameters? This is just kind of because we just want to see what the behavior is. And the reason that we picked these two different benchmarks is because these are going to have very different spectral shapes, as I'll get to in a second. The red benchmark, this is occurring at an earlier time, corresponding to a temperature of 3 keV in the visible sector. Here, we're less constrained, so we can take an alpha of 0.05, but we're just going to take the same values for kappa and beta on H star for comparison purposes. And then I've also shown here what the spectrum looks like for inflation with a tensor scalar ratio of 10 to the minus 3. Um, and this is chosen such that the maximum amplitude of the B-mode like power spectrum is going to have the same amplitude. So that's how these benchmarks were chosen, which you'll see in a sec. And then the other thing I should point out is that this gray CMB sensitivity region, this is really showing the kind of the domain of support for the window function, that FFL squared thing that entered into the definition of the CLBBs. So if you'll recall, that was the CLBVs were this logarithmic integral of the power spectrum convolved with this FL squared kernel. So only the portions of the power spectrum that are in this region are going to contribute really non-trivially to that integral. And that's going to help us understand what the spectral shapes look like in a few slides. Okay, so before I get to the results, were there any questions?
Aurora, I had a question a couple of slides back on page 21. Um, you've got two results there with K less than or equal to KB. I'm assuming that's a typo or I've misunderstood
Oh,
something.
yeah, no, that's a typo. I'm sorry about that. That's okay, this should be K greater than KP, the bottom
That's
one.
what I assumed based on conventional ordering, but I just
Yeah.
checked that, yeah, that I wasn't being dumb.
No, no, you're not being dumb. I was
Fine.
being dumb. I'll fix that. Thank you.
Sure.
Can I ask a quick question about this also? So you have this intermediate regime with the sub-horizon scales, which are super bubble, where you've like it from the plot, it kind of just looked like you had some, maximum K which you want to go up to super horizon, then you're stitching it, linearly to where you believe the sub-horizon regime should take over. And you made, I think,
Yeah.
the comment that it's not going to matter very much, but if I look at that that's right in the regime where you're sensitive, right? That scaling. So does it end up not mattering, or is it you're really just caring about the peak of the spectrum at the end of the day? Or
Yeah. It's really most of it's gonna come from the peak. For this green benchmark. Um, Yeah, for the red benchmark, it's not going to matter because here we've already taken over the super horizon scaling, so it's not going to matter at all. For the green benchmark, the majority is going to come from the peak, and that's part of the calculation that we trust fully. So I I don't think it'll change terribly.
okay, so the key quantity really is K, like KP, I guess. Is that the K of the peak, right? That you so that you're
Yeah,
that you have that number, uh, roughly.
yeah.
Yeah. Okay.
Yeah, I highly doubt it would change a lot. Yeah. All right. So I guess go ahead and show what the spectra look like now, and we'll start with the one that was asked about, the 1 eV benchmark. Um, so yeah, and I'm comparing it against what the spectrum looks like for inflation with this tensor scalar ratio of 10 to the minus 3. So compared with the inflationary one, we're peaking at, just slightly afterwards, which kind of makes sense. 1 eV is very, very late. Um, so it makes sense that the peak is only on slightly smaller scales. Um, but on larger scales and smaller scales, we have less power than in the inflationary case, and we really have like nothing in the reionization peak. So this can really be understood from the shape of this guy. Most of the power is coming from the peak, and then we're falling off in the subhorizon and the superhorizon tails. So I think if you change the parameterization for the intermediate region, um, this might look slightly different, but I think the peak of this thing would be about the same. All right. And then this is the one for the other benchmark. So this is the 3 keV guy. So here we're peaking on much smaller scales as compared with the inflationary one, and we're falling off on the larger scales. And the shape of this can kind of be understood from, again, here we're doing everything just with the super horizon tail. So it makes sense that, most of the power here is coming from smaller scales. It's, yeah, I think looking at that kind of gives a feeling for why this looks the way it does. Um, so here is a color map of, you know, what the B-mode spectra would look like if you change the well, if you change the time that they're happening. Here we fix the other parameters. So, some of these are going to be ruled out. The ones way up here are going to be ruled out on the basis of, other constraints, but this is just to show how the shape changes. So here on the red ones, as we go up here, we're still just doing everything with the super horizon tail. When it starts to curve down like this, we're starting to sample from the peak of the tensor power spectrum and the sub horizon tail a little bit. So that's why that's changing. Right. I think I've kind of talked about this, but maybe I'll go ahead and just explain again how to explain the spectral shape. So it's this competition between P sub H, which is, peaked on some particular scales and falls off in the sub and super horizon regime. And then this F of L squared, which is, has support in that gray region of the plots and falls off very sharply on smaller scales and slightly less sharply on larger scales. Um, so it's kind of this competition between these two, the Bessel function suppression here, and then the whatever you want to call it, suppression there, away from the peak. Um, so compared with inflation, you're having some scale invariant power spectrum. So the dominant contribution is going to come from whenever this F of L squared peaks, and this thing peaks around 0.01 inverse megaparsec. So you expect the inflationary one to also peak there. Very roughly, that corresponds to an L of 100. It's not like a strictly linear mapping, but roughly that corresponds to a multipole of 100, which is, yeah, indeed what you see for the inflationary case. Um, versus for the power spectrum, or sorry, for the phase transition, the power spectrum is suppressed on larger scales and smaller scales relative to the peak. Um, in general, the dominant contribution is going to come from smaller scales relative to inflation, unless you have something that's super late, despite the suppression in the window function there. So generically, you're going to expect the spectrum to peak at larger L, which is indeed what you see here. Um, less so here, just because this is such late time. It's, the peak is kind of close to the inflationary one, but yeah, in general, the spectrum is going to peak at larger L. Okay. Um, before I talk about the gravitational wave signal, is there anything with the plots, or questions? Nope. Okay. So I think I have like 10 minutes left, which is perfect. We'll talk about the gravitational wave signal. Um, right. So the same tensor perturbations that give you this B-mode pattern also are going to contribute to the stochastic gravitational wave background. So in principle, this can be a complementary signature of this scenario. Um, but for these two benchmarks I showed, the frequency is going to be way too low that the only place you would see this sort of thing is in the B-mode polarization. But in principle, right. So I'm not going to go into gory detail with how I'm going to calculate the gravitational wave signal. I'll just mention that I'm going to parameterize the energy density in gravitational waves by the spectral density parameter, which is the energy density in gravitational waves per logarithmic frequency interval normalized to the total energy density. Um, Initially, at the time of the phase transition, I can compute what the energy density in gravitational waves is by taking this real space 2-point function of not the tensor perturbation, but its derivative with respect to conformal time, which I could calculate if once I calculate the power spectrum of this H prime, which is slightly different than the power spectrum of H itself. For the subhorizon modes, this is just like k squared times the power spectrum of the H itself. And for the superhorizon modes, it's actually like the same thing. But right, calculating this thing is actually a little bit easier because there's no subtlety with the superhorizon modes, because although this is too much detail, I calculated it. So I can write down what my initial spectrum is, doing the same song and dance as before, and then I can evolve that signal to today. And I get this prediction for the spectral density today as a function of my thermal phase transition parameters. And this is the same delta function that appeared before. So now I'm going to plot this for the two benchmarks that we followed. So the red one is the 3 keV benchmark, and the green one is the later time guy. Um, and then I'm also showing here the prediction from inflation for the tensor scalar ratio of 10 to the minus 3. Um, right. And then also, proposed sensitivities. But as I said, really these are peaking at much too low frequencies for this to really be a target for the peak. I mean, if you have this much power, you could potentially see it in the subhorizon tail there. But
Sorry,
yeah, but the main thing,
where are the current PTA measurements on this if you interpret them in this way?
oh, where are I think they're the current PTA limits on this.
I
Sorry.
mean, they must be like around SKA, right? But I don't know. There must be higher amplitudes if you interpreted the signal as. stochastic gravitational wave and not from supermassive black holes.
Oh, yeah. Okay, I see what you're saying, like in the nanograv regime. Um, yeah, I think it's higher amplitude. I I I that's my guess as to why we didn't plot it, because otherwise I don't know why we wouldn't have plotted it. So my guess is it's higher amplitude.
Okay.
Um, yeah, but the nice thing with the gravitational wave signal is it's if you see the B-mode polarization, like if we were to measure something like this, but then we don't measure this, that would tell you that whatever we saw was not from a phase transition. It was truly primordial inflationary B-mode polarization. So this gives like a cross check. Also don't know why that slide is a different color. Um, okay, so good. I will wrap up with a summary, and then some comments on future directions, and then questions. So in summary, I've tried to show that tensor perturbations from a first order phase transition can surprisingly actually maybe produce B-mode polarization on observable scales. If you choose the phase transition parameters right, and if you can actually find some microphysics model to give you those parameters, then the signal strength can actually rival inflationary predictions if you have something that's late time and strong. Maybe we could test this with CMB stage 4. Um, it's not, a death knell for, having an observable from inflation because the spectral shape is distinct from the inflationary one. So if you see a B mode signal and, you know, then you can measure on multiple angular scales, which actually I don't know how difficult that is. But you can if you make enough measurements, you can tell it to like flesh out what the spectral shape is. You can tell this source apart from inflation. Um, or you can also look for the complementary gravitational wave signal to act as a cross check. Um, in terms of future directions, so yeah, can you actually get these phase transition parameters? Great question. We're working on it. Hope to have an answer soon. And then, of course, there are lots of other sources of tensor perturbations. Here, we just focused on the bubble collision stage of a very particular type of first order phase transition. Just it was the easiest thing to compute, but now you could compute the signal from the sound wave stage or the the hydrodynamic turbulence. You could look at cosmic strings or domain walls. Um, and then the other thing is, you could try and do some model dependent limits, or just in general, I was kind of surprised to find how few limits on late time phase transitions happening in the dark sector, you can really constrain. So these are things that we're thinking about now. Um, yeah, and that's just about it.
Thank you very much. Yeah, any more questions?
Can I ask one question?
Yeah.
So can you go back to the numerical results where you showed that plot? You had a plot where you had, I think, those colorful plots from. Yeah, the one on the next slide, I think.
This one?
Yeah, this one. So okay, so what I'm wondering is, so to which range of temperatures or T star are you sensitive now with the CMB for the phase transitions? So what kind of the ballpark of T star?
Um, yeah, so it's really dependent on what the other parameters are. Um, Here I fixed it to these values, and for these values, um, I guess the black line or up is what we would be sensitive to. Um, but these are actually ruled out for these parameters for other things. Like we have constraints on this size of alpha at, this time from various things, delta and effective, CMB spectral distortions, just the scalar perturbations that this dark sector phase transition would give. So
Okay.
yeah,
So you're basically looking at a plot that would be something like 1 kilo electron volt and smaller temperatures. So if you now have your
yeah,
supercooled phase transition, what critical temperature does that correspond to? So if I basically think about electroweak phase transition, do I have to which may be supercooled in a model like a scale invariant model? You can have supercooled phase transitions there. Do I have to worry about that? Do I have to think about constraints from CMB?
yeah. I mean, if you're doing this with the electroweak phase transition, definitely. Um, yeah, I mean, if you're doing things at 1 kV, I think it really has to be in a dark sector. Otherwise, you have too large, just the heating of the standard model plasma, you'd run into issues with ineffective and spectral distortions, I think, at that temperature.
Oh, okay. So it's more like for phase transitions in the dark sector. Okay, good. Yeah,
Yeah,
thanks.
yeah. If you were doing it at like 1 MeV, I think you'd be, or 10 MeV, I think you'd be fine in the standard model. But then, yeah, it's very difficult you need a lot of power to overcome the suppression and the Bessel functions to have something observable at that temperature or at that time.
Okay, good. Yeah, thanks.
Hmm.
Yeah, so I had a question. So I'll go back to I think Mikhail's point. I think you need an exclusively some kind of a secluded dark sector model to do this, because otherwise, I mean, if you have any connection with the standard model, then at that temperature, I mean, that's what I'm wondering. If you like, how complicated does the dark sector have to be in order to?
Yeah, it essentially has to be secluded or like very, very weak portal couplings.
Yeah.
Wondering, Archel has been discussing some model where they had scale invariant model, and they looked at the electroweak phase transition, but because it was scale invariant, it was only the onset was in the around the QCD phase transition, around 100 MeV, and then it was supercooled further. Um, so maybe that could get you down then in that ballpark, but I don't know. I don't remember what was the parameters.
Huh. Yeah, I think at the QCD scale, even if it's super super cooled, I think that might be too high. But I'm not sure or too early. You know what I mean?
Yeah, that's Josh's work. They end up reversing the electroweak and QCD transitions. So you get like
Mm,
bubbles, which are sort of stabilized by the Higgs or something, but I think he's still working on that.
right. If you reverse them, then QCD becomes first order. Is that
I'm not sure.
okay?
I had another question. So you mentioned this, the spectral shapes would be the thing that you would use to tell apart inflationary B modes and the from the ones from first order phase transition. But I don't have these plots sort of committed to memory. So like, how does it compare to the lensing beam mode? Are there like parts of parameter space where you would get like a sort of semi-degenerate spectrum to the
Yeah,
lensing beam
no,
mode?
that's a great question, and I should have maybe made them on the same plot because actually the this benchmark turns out to be very close to the shape of the lensing one. Actually, it's kind of difficult to see because this is plotted as this DLBB rescaled with the LL plus one versus I think in the original I was plotting right. Oh yeah, they are the same. Okay, so the lensing is let's see. At 10, it's like 10 to the minus 5, and that's 1,000. It's like 10 to the minus 2. Okay, 10 to the minus 5. Oh, okay. 1,000, 10 to the minus 2. Okay, so if you had, if this was amplified by a few orders of magnitude, it would match on to the lensing one. It roughly goes like alpha squared at small alpha. So I think in order to reach that, you would need to either blow up alpha by like 1.5 orders of magnitude, or I don't know. If you make it at a slightly later time, that could also help a lot. But yeah, the slope of this is very similar to the lensing.
And this is slightly orthogonal, I guess, to what you were talking about, but I haven't followed this very closely. The data you were showing on the B modes from Bicep and ACT and stuff, there seemed to be some region where there was quite a lot of scatter, at least compared to the error bars that were shown. Is this something that people are discussing in this field, or like SPT and I
Mm.
guess polar bear? I can't quite tell the colors apart, but yeah, yeah. It's at the high
Um,
multivolts.
yeah, it's difficult to tell. I I know probably less about the experimental side than I probably should. But we are talking it to two experimentalists now, trying to make predictions from this more concrete. So I'll ask what the status of, the scatter on these error bars is.
All right, so I think we exhausted the questions. So yeah, I'll stop